Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is motor connection diagrams. Our objective is to learn to read and interpret motor connection diagrams. We'll examine Y and delta configurations and dual voltage motors. Although a related topic, this lecture does not discuss multi-speed motors. This lecture operates under the assumption the viewers watch the electromagnetic interaction, the rotating magnetic field, and the motor nameplates lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. You'll recall, an electromagnet is established in a coil of wire whereby the polarity of the resultant magnetic field is dependent upon the direction of current flow, and the strength of the resultant magnetic field is dependent upon the amount of current flow. You'll additionally recall three-phase AC synchronous and induction motors are powered by a rotating magnetic field in the stator, where the physical placement of windings around the circular perimeter of the stator, and the order, frequency, and polarity with which these windings are energized determines the direction and speed of the rotating magnetic field. Swapping applied phase sequence of any two phases would see the motor reverse direction. During the course of the aforementioned lectures, we restricted ourselves to discussing only the magnetic and physical aspects of the stator windings and largely ignored the electrical aspects. Our intention today is to rectify this oversight by discussing how one wires stator windings in a Y or a delta configuration or for low or high voltage systems. Bottom line up front, motor connection diagrams aren't paintings, poems, or pottery to appreciate, critique, or interpret as you see fit, and you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise you'll hurt the motor, your instruments, or yourself. An improperly wired motor might be damaged, or at the very least, not work well if it's improperly wired. This fact necessitates a brief note of caution before we begin. Do not assume these connection diagrams and terminal numbers as illustrated in this lecture are universal in nature. A thick, tangled jungle of peculiarities exist, especially for older motors and motors manufactured by shoddy companies in backward countries. It is incumbent upon you to determine the proper connection diagram for the specific motor of interest. First among our tasks is to have a working description of three-phase AC and define the term dual voltage. As a brief overview, three-phase AC is characterized by three sinusoidally oscillated waveforms with equal magnitude and frequency, phase shifted from one another by a relative 120 degrees. A single three-phase AC system, in effect, offers a choice of two voltages: the lower line-to-neutral voltage and the higher line-to-line voltage. Line-to-line voltage is always square root 3, or roughly 1.73 times that of line-to-neutral. Light industrial three-phase AC inside the United States is characterized by a 120-volt line-to-neutral and a 208-volt line-to-line value. Three-phase AC allows two basic options: Y-configured loads, which experience the lower line-to-neutral voltage, and delta-configured loads, which experience the higher line-to-line voltage. This is not what I mean by the term dual voltage. A single three-phase AC system with two available voltages, line-to-neutral and line-to-line, is still a single system. The term dual voltage more appropriately means two system voltages. Manufacturers offer dual voltage or dual system motors so the products can meet the needs of industrial applications in various countries characterized by different electrical distribution voltages. One system is designated as the low voltage option with its own line-to-neutral and line-to-line voltages, whereas the other is designated as the high voltage option with totally different line-to-neutral and line-to-line voltages. As I'll soon demonstrate, low voltage configurations are associated with parallel windings, whereas high voltage configurations are associated with series windings. It should be noted all entries in a motor nameplate, unless explicitly stated otherwise, assume the higher line-to-line voltage, regardless if that motor is configured in Y or delta fashion. I say again, all entries in a motor nameplate assume the higher line-to-line voltage, regardless if that motor is configured in Y or delta fashion. Manufacturers typically offer a limited range of options, normally restricting themselves to the following 6 choices: 3-lead Y-configured motors, 3-lead delta-configured motors, 6-lead motors, 9-lead Y-configured motors, 9-lead delta-configured motors, and 12-lead motors. We'll examine each option in detail in a moment, but let's divide these into general classes regarding their electrical configuration and whether or not these motors are intended for single or dual voltage systems. First, electrical configuration. As implied by their titles, 3-lead Y-configured motors and 9-lead Y-configured motors are permanently pre-configured as Ys, and there is nothing you can do about it. They are always Y-configured motors. Similarly, as implied by their titles, 3-lead delta configured motors and 9-lead delta configured motors are permanently pre-configured as deltas, and there is nothing you can do about it. They are always delta configured. 6 and 12-lead motors, as I'll soon demonstrate, can be hooked up in either Y or delta fashion. Let's now identify which motors are intended for use with single voltage systems or dual voltage systems. All 3-lead and all 6-lead motors are intended for single voltage operation, whereas 9 and 12-lead motors are intended for dual voltage operation. If you think about it, we are presented with two independent choices, Y or delta, and single or dual voltage, which effectively gives us 12 different options. 3-lead Y configured motors, 3-lead delta configured motors, 6-lead motors configured as Ys, 6-lead motors configured as deltas, 9-lead Y configured motors in low voltage configuration, 9-lead Y configured motors in high voltage configuration, 9-lead delta configured motors in a low voltage configuration, 9-lead delta configured motors in a high voltage configuration, and finally, the most flexible options, 12-lead motors configured as low voltage Ys, 12-lead motors configured as high voltage Ys, 12-lead motors configured as low voltage deltas, and finally, 12-lead motors configured as high voltage deltas. Let's begin with an analysis of 3-lead Y configured motors. As implied by their titles, 3-lead Y configured motors are permanently pre-configured as Ys, and there's nothing you can do about it. They are always Y configured. Electrically, one might visualize 3 separate windings permanently pre-bonded together in a Y fashion at a central node. 3 external leads, 1, 2, and 3, allow connection to primary voltage L1, L2, L3, where swapping any 2-plied phase sequences reverses rotational direction. One can almost say the exact same thing about 3-lead delta configured motors. As implied by their titles, 3-lead delta configured motors are permanently pre-configured as deltas, and there's nothing you can do about it. They are always delta configured. Electrically, one might visualize 3 separate windings bonded together in a delta fashion. 3 external leads at the corners 1, 2, and 3 allow connection to primary voltage L1, L2, and L3, where swapping any 2-plied phase sequences reverses rotational direction. While we've got these visualizations right in front of us, let me make an important observation about electrical instrumentation and 3-phase AC motors. These are 3-lead motors, and one does not ordinarily have access to the internal connections and individual windings. This implies certain electrical properties might be easier to obtain depending upon electrical configuration, and others less so. Allow me to demonstrate. As you are no doubt aware, voltmeters are placed in parallel with the item under test. A 3-lead Y configured motor typically hides the central node inside the motor. Thus, it is ordinarily impossible to measure voltage across an individual winding. Similarly, you are no doubt aware ammeters are placed in series with the item under test. A 3-lead delta configured motor permanently bonds the windings together in a delta configuration, and windings cannot ordinarily be broken apart to insert the ammeter in series and measure current through an individual winding. This is to suggest that measuring individual voltage winding in Y-configured motors is hard, as is measuring current through an individual winding in a delta-configured motor. Luckily, some properties are easier to obtain dependent upon configuration. Measuring current through an individual winding in a Y-configured motor is easy. An ammeter can always be inserted in series between the source and the external lead of the winding of interest. Similarly, measuring voltage across an individual winding in a delta-configured motor is easy. Voltage is a 2-point measurement. A voltmeter would be placed across the 2 external leads of the winding of interest. In summary, it's easy to measure current through a Y-configured winding, but hard to measure voltage across it. The opposite can be said about delta-configured motors. It's easy to measure voltage across a delta-configured winding, but hard to measure current through it. For this reason, when working with balanced 3-phase AC systems like 3-phase AC motors, one customarily employs what is known as the single wattmeter method, which utilizes measurements entirely external to the motor. A line-to-line voltage measurement is external to the motor, as is a line current measurement. Total apparent power delivered to the motor is equal to square root 3 times the line-to-line voltage times the line current, regardless of the electrical configuration of the motor, Y or delta. Related to today's topic of discussion, motor connection diagrams, you should understand that certain configurations preclude invasive inspection, and some electrical properties aren't as easily obtained as one might think. This being said, line-to-line voltage and line current readings are always an option because they're entirely external to the motor, and the single wattmeter method can be used to calculate apparent power delivered to the motor under inspection, regardless of configuration, Y or delta. Let's now examine 6-lead motors. These motors consist of 3 individual windings with 2 ends each. Winding 1-4, winding 2-5, winding 3-6 are isolated from one another, and both terminals of each winding are externally accessible. 6-lead motors are considered single voltage motors, and that they're intended to be used with one predetermined electrical system with an associated line to neutral and line to line voltage. When configured as Ys, terminals 4, 5, and 6 are tied together at a single node, and primary voltage L1, L2, and L3 are connected to terminals 1, 2, and 3, where swapping any 2 applied phase sequences reverses rotational direction. In the Y configuration, the windings would experience a smaller line to neutral voltage. A motor connection diagram illustrating a 6-lead motor setup might look something like this: L1 to 1, L2 to 2, L3 to 3, and 4, 5, and 6 tied together. Another option exists. When configured as deltas, terminal 4 is tied together with 2, 5 is tied together with 3, and 6 is tied together with 1. And primary voltage L1, L2, and L3 is connected to the conjoined terminals 1, 6, 2, 4, and 3, 5, where swapping any 2 applied phase sequences reverses rotational direction. In the delta configuration, the windings would experience the higher line-to-line voltage. A motor connection diagram illustrating a 6-lead motor set up as delta might look something like this: L1 to 1 and 6, L2 to 2 and 4, and L3 to 3 and 5. This is to suggest that a 6-lead motor is slightly more flexible than a 3-lead Y or a 3-lead delta because it can act as a Y or a delta depending upon the manner in which it is connected. In fact, an extremely popular reduced voltage starting method known as a Y-start delta run reduced voltage starter takes advantage of the adaptable nature of this type of motor. As implied by the title, a Y-start delta run reduced voltage starter starts the motor in a Y configuration, such that each winding experiences a smaller line to neutral voltage and thus draws smaller inrush current. Then, after a predetermined time allowing the motor to accelerate, the Y configuration is broken and reassembled as a delta, so each winding experiences the larger line-to-line voltage, thus drawing more current. This 2-stage start reduces inrush current and modifies the starting torque of the motor under its direction. We'll examine Y-start delta run reduced voltage starters in greater detail in later lectures. While we've got these visualizations of 6-lead motors and Y and delta configurations in front of us, allow me to reiterate an earlier observation. This is not art class, and you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise you might damage the motor, your equipment, or yourself. As presently illustrated, Y-configured 6-lead motor ties together leads 4, 5, and 6, and the delta configuration goes 1, 4, 2, 5, 3, 6 when traveled in a clockwise fashion. Consider the following subtle modifications and their not so subtle consequences. Consider a Y-configured motor with leads 4, 5, 3 forming the central node of the Y. There's still 3 windings in a Y configuration, but this won't work. You know, winding 3, 6 is flip-flopped. Similarly, consider a delta configured motor going 1, 4, 2, 5, 6, 3 when traveled in a clockwise fashion. There's still 3 windings in a delta configuration, but this won't work. You'll again note winding 3, 6 is flip-flopped. You might initially think that any end of any winding will do equally as well as any other, but they don't for a rather important reason. You'll no doubt recall that current direction influences magnetic polarity. Connected in this improper fashion, winding 3, 6 would be a north when it's supposed to be a south, and vice versa, hopelessly wrecking any chance of establishing a smoothly rotating magnetic field in the stator. Follow the connection diagrams exactly as illustrated. Moving on, let's now examine 9-lead motors, of which there are 2 varieties: 9-lead Y-configured motors and 9-lead delta-configured motors. As applied by their titles, Ys are always Ys and you can't do anything about it. The same thing can be said about deltas. 9-lead motors, however, have the advantage of being applicable for dual voltage operation. Bottom line up front, low voltage configurations are associated with windings in parallel, whereas high voltage configurations are associated with windings in series. Allow me to demonstrate. Consider a 9-lead Y-configured motor consisting of 6 windings, 3 independent and isolated with both ends accessible, and 3 permanently bonded together in a Y configuration with only one ending of each winding accessible. Windings 1, 4, 2, 5, and 3, 6 can be positioned as needed, whereas windings 7, 8, and 9 are a conjoined set of 3. In a low voltage configuration, 4, 5, and 6 are tied together, forming another Y. Then 1 is tied to 7, 2 to 8, and 3 to 9, forming an almost overlapping double Y in parallel with one another. Primary lines L1, L2, and L3 would be connected to conjoined terminals 17, 28, and 39, where swapping any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, low voltage Y configurations are sometimes known as YY configurations. Given each winding is a balanced load, there is no need to join the center of the two Ys. It should be noted that parallel impedances add more paths for current. This is why the low voltage entry in a motor nameplate has twice the current as the high voltage configuration. A motor connection diagram illustrating a 9-lead Y configured motor set up in the low voltage configuration might look something like this, where L1 goes to 1 and 7, L2 goes to 2 and 8, and L3 goes to 3 and 9, and 4, 5, and 6 are tied together. In a high voltage configuration, 4 is tied to 7, 7 to 8, and 6 to 9, forming a large Y with each leg of the Y being a series combination of two windings. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, high voltage Y configurations are sometimes known as big Y configurations. It should be noted that series impedances add up. This is why the high voltage entry on a motor nameplate has half the current draw as a low voltage configuration. A motor connection diagram illustrating a 9-lead Y configured motor set up in the high voltage configuration might look something like this: L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, and 6 to 9. Similar things can be said about 9-lead delta configured motors. Low voltage configurations are associated with windings in parallel, whereas high voltage configurations are associated with windings in series. Allow me to demonstrate. Consider a 9-lead delta configured motor consisting of 3 sets of paired windings permanently joined together. Visualizing 9-lead deltas is a little difficult unless you just pick a direction and stick with it. In this case, let's go clockwise. Winding 9-1 is joined to windings 1-4 at corner 1. Winding 7-2 is joined to winding 2-5 at corner 2. And finally, winding 8-3 is joined to winding 3-6 at corner 3. You can see how each pair of conjoined windings in a 9-lead delta configured motor essentially forms two legs of a partial triangle. Terminals 9 and 4, 7 and 5, and 8 and 6 are ends, whereas terminals 1, 2, and 3 are the corners. In a low voltage delta configuration, one overlaps the two legs to form one triangle on top of another. Ends 6 and 7 are tied to corner 1. Ends 4 and 8 are tied to corner 2. And finally, ends 5 and 9 are tied to corner 3. Primary lines L1, L2, and L3 would be connected to conjoined terminals 617, 428, and 539, where swapping in a two-applied phase sequences reverses rotational direction. For hopefully obvious reasons, low voltage delta configurations are sometimes known as delta-delta configurations. It should again be noted that parallel impedances add more paths for current. This is why the low voltage entry in a motor nameplate has twice the current as a high voltage configuration. A motor connection diagram illustrating a 9-lead delta configured motor set up in the low voltage configuration might look something like this, where L1 goes to 617, L2 goes to 428, L3 goes to 539. In a high voltage delta configuration, we don't overlap the two-legged triangles, but rather the ends of the partial triangles simply join hands. 4 is tied to 7, 5 to 8, and 6 to 9, forming a large delta, with each leg of the delta being a series combination of two windings. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping in any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, high voltage delta configurations are sometimes known as big delta configurations. It should again be noted that series impedances add up. This is why the high voltage entry on a motor nameplate has half the current draw as a low voltage configuration. A motor connection diagram illustrating a 9-lead delta configured motor set up in the high voltage configuration might look something like this: L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, and 6 to 9. Before we move on to examine 12-lead motors, allow me to discuss a feature unique to low voltage Y and delta configured motors. You note each leg in a low voltage Y or delta is a parallel arrangement of two windings. Parallel configurations draw more current because there are more paths for current flow. If somehow we remove one path, at least temporarily, less current will flow. Another type of reduced voltage starting method, called a part winding reduced voltage starter, takes advantage of this fact. Similar in nature to a Y-start delta run reduced voltage starter, a part winding reduced voltage starter has two defined stages: a start and a run stage designed to reduce inrush current and modify the starting torque of a motor under its direction. A part winding reduced voltage starter starts a low voltage configuration with only one set of windings, such that each large impedance path draws smaller inrush current. Then, after a predetermined time allowing the motor to accelerate, the second set of windings is brought in parallel, thus drawing more current. Here's an example of a part winding reduced voltage starter applicable for a low voltage Y configuration. We'll examine part winding reduced voltage starters in greater detail in later lectures. Let's now examine 12-lead motors, the most flexible of options. 12-lead motors are characterized by 6 individual isolated windings with both ends of each winding accessible. Winding 1-4, 2-5, 3-6, 7-10, 8-11, and 9-12. Given your understanding of the previous content, you'll no doubt see the utility of 12-lead motors and that they are truly customizable and can be configured as low voltage Ys, high voltage Ys, low voltage deltas, or high voltage deltas. As with 9-lead Y configured motors, one configures a 12-lead motor as a low voltage Y by making 2 small Ys by conjoining terminals 4, 5, and 6, and 10, 11, and 12. Then one overlaps the Ys in a parallel configuration by tying together leads 1, 7, 2, 8, and 3, 9. Primary lines L1, L2, and L3 would be connected to conjoined terminals 1, 7, 2, 8, and 3, 9, where swapping any 2 applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a low voltage Y is sometimes referred to as a YY configuration. A motor connection diagram illustrating a 12-lead motor set up for the low voltage Y configuration might look something like this. L1 goes to conjoined terminals 1, 7, L2 goes to 2 and 8, L3 goes 3 and 9, 4, 5, and 6 are tied together, as are 10, 11, and 12. Similarly, one configures a 12-lead motor as a high voltage Y by making a large Y by conjoining terminals 4 and 7, 5 and 8, and 3 and 9 to make 3 series branches. Then one joins leads 10, 11, and 12 in the center. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping any 2 applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a high voltage Y is sometimes referred to as a big Y configuration. A motor connection diagram illustrating a 12-lead motor set up in the high voltage Y configuration might look something like this. L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, 6 to 9, and finally 10, 11, and 12 tied together. In order to configure a 12-lead motor as a low voltage delta, one would make 2 overlapping deltas by conjoining terminals 1, 7, 6, 12, 4, 10, 2, and 8, and 5, 11, 3, and 9. Primary lines L1, L2, and L3 would be connected to conjoined terminals 1, 7, 6, 12, 4, 10, 2, and 8, and 5, 11, 3, and 9, where swapping any 2 applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a low voltage delta is sometimes referred to as a delta-delta configuration. A motor connection diagram illustrating a 12-lead motor set up in the low voltage delta configuration might look something like this, where L1 is applied to 1, 12, 6, and 7, L2 is applied to 2, 10, 4, and 8, and L3 is applied to 3, 11, 5, and 9. You note the numerical arrangement of the terminals for a low voltage delta configuration is different than that of the previous Y configurations. As illustrated, 7, 8, and 9 is on top, and it goes 6, 4, 5, and 12, 10, 11 left to right. This prevents lines crossing each other in the diagram. You should note that not all manufacturers use this technique, so be prepared for variations on this theme. Lastly, one configures a 12-lead motor as a high voltage delta by making a large delta by conjoining terminals 4, 7, 5, 8, and 3, 9, making 3 series legs. Then one joins leads 1, 12, 2, 10, and 3, 11 as the corners. Primary lines L1, L2, and L3 would be connected to conjoined terminals 1, 12, 2, 10, and 3, 11, where swapping any 2 applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a high voltage delta is sometimes referred to as a big delta configuration. A motor connection diagram illustrating a 12-lead motor set up in the high voltage delta configuration might look something like this. Again, you'll note that the numerical arrangement of the terminals for a high voltage delta configuration is different than the other configurations, Y or delta. You note it goes 4, 5, 6 left to right this time. This prevents lines crossing each other in the diagram. Not all manufacturers use this technique, so be prepared for variations on this theme. While we've got these visualizations right in front of us, let me reiterate an earlier point. This is not art school, and you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise you might damage the motor, your equipment, or yourself. Windings and terminals are not equivalent and cannot be substituted one for another or hooked up backwards. For example, if we swapped winding 1-4 with 3-6 in a low voltage Y configuration, this would not work because winding 1-4 is intended for phase L1 with a phase shift of 0 degrees, whereas winding 3-6 is intended for phase L3 with a leading phase shift of positive 120 degrees. I must remind you that winding 1-4 and 3-6 occupy different physical locations around the circular perimeter of the stator, and nearby windings are dependent upon 1-4 and 3-6 of not only doing their job, but doing their job at exactly the right time. Improperly connected 1-4 would peak too early and 3-6 too late. The incorrect electrical connection of these windings would result in a hitch or an outright disruption of the rotating magnetic field. Similar cautions can be made against hooking windings in a reverse fashion since current direction influences magnetic polarity. Backward windings would be norths when they're supposed to be souths and vice versa. If you think about it, a single backwards winding in a circle of 11 properly connected windings is the one jerk that ruins the whole show for everybody. You know which lab partner I'm talking about, don't you? All right, that's about it for today. Before we go, a brief summary. Motor connection diagrams illustrate how to configure a motor as a Y or a delta, and whether they are or are not suitable for dual voltage operation. 3-lead Y configured motors and 3-lead delta configured motors are not customizable and are intended for single voltage operation. 6-lead motors are also intended for single voltage operation, however can be configured as Ys or deltas. This gives us two options: 6-lead motors configured as Ys or 6-lead motors configured as deltas. 9-lead Y configured motors and 9-lead delta configured motors are not customizable, however they can be used for dual voltage operation. This gives us two options each: 9-lead low voltage Ys, 9-lead high voltage Ys, 9-lead low voltage deltas, 9-lead high voltage deltas. 12-lead motors are fully customizable and can be used in dual voltage operation. A single 12-lead motor effectively gives us four options: 12-lead motors as low voltage Ys, 12-lead motors as high voltage Ys, 12-lead motors as low voltage deltas, and finally 12-lead motors as high voltage deltas. I should note there exist Y delta configurations, which as the name implies is a Y inside a delta. This is a barrel of monkeys I do not wish to open, but with a little bit of thought and imagination you could see how a 12-lead motor could be configured as such if you wanted to. Lastly, I should remind you that certain types of reduced voltage starters make use of different motor configurations to reduce inrush current and modify the starting torque of a motor under their direction. Y-start, delta run reduced voltage starters, as implied by their title, necessitate a motor that can be set up as a Y or a delta. This method can only be used for 6 or 12-lead motors. Part winding reduced voltage starters initially use one set of windings during the acceleration phase before the other set is brought in parallel. Only motors with parallel windings, i.e. low voltage configurations, can make use of this technique. This leaves 9-lead low voltage Ys, 9-lead low voltage deltas, 12-lead low voltage Ys, and 12-lead voltage deltas as available options. We'll examine these and other reduced voltage starting techniques like primary resistor reduced voltage starters and soft starters in later lectures. Finally, motor connection diagrams are not poems, songs, or paintings to be debated, interpreted, or modified. Follow the connection diagrams exactly as illustrated, otherwise you might damage the motor, your equipment, or yourself. In conclusion, this lecture discussed motor connection diagrams. We'll examine 3, 6, 9, and 12-lead motor connection diagrams and discuss dual voltage motors, Y and delta configurations, and briefly discussed how motor connection diagrams may influence the suitability of certain types of reduced voltage starters. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.